What if the largest planet in our solar system hides storms that have been raging since before human history began? Tonight, we drift gently toward Jupiter and uncover the quiet, surprising secrets hidden inside this enormous world. Welcome to this calm journey through the world of Jupiter. As you settle in and let your body relax, we will slowly explore the largest planet in our solar system in a gentle, sleepy way. You do not need to remember any numbers or details. Just let the images and ideas drift past like clouds while you rest. Jupiter is often shown as a striped ball with a red storm, but the real story is much richer and more surprising. It is a world so big that more than 1,000 Earths could fit inside it. It spins faster than any other planet, pulls on comets and asteroids, and shelters dozens of moons that are like tiny planets of their own. Deep inside, its gases are squeezed into strange forms of matter, including oceans of metallic hydrogen that we cannot see directly. All around it, a strong magnetic field shapes space, traps particles, and paints bright auroras near its poles. As we move through this story, we will visit each of these layers and regions in a calm, unhurried way. We will start with Jupiter's enormous size and gentle pull on the solar system. Then we will sink inward, imagining what happens as the gas thickens, the pressure grows, and hydrogen turns into something like liquid metal. After that, we will rise again to wander among the storms, bands, and polar cyclones that wrap around the planet. From there, we will glide outward into the invisible magnetic bubble that surrounds Jupiter and powers its glowing auroras. Finally, we will visit some of its most famous moons, like Io with its volcanoes, Europa with its hidden ocean, and the larger frozen worlds of Ganymede and Callisto. Each step of the journey will be gentle and slow, with short sentences and simple ideas, so your mind can follow easily even as you grow sleepy. You can imagine that you are aboard a quiet spacecraft, floating weightlessly, watching these giant shapes and distant moons pass by the window. There is nothing you need to do and nowhere you need to go. Just listen, breathe slowly, and let Jupiter's calm, distant world keep you company as you drift toward sleep. Jupiter is the largest planet our species has ever discovered up close. When you compare it to Earth, the difference feels almost unreal. Jupiter is wide enough to fit more than 11 Earths across its belly, and roomy enough to swallow over 1,000 Earth-sized worlds inside its volume. It is so massive that it contains more than twice the material of every other planet in the solar system combined. If our sun were the king, Jupiter would stand proudly as the giant that guards the kingdom. Its presence is powerful enough to tug at comets, push asteroids, and shape the orbits of its many moons. But this enormous world is not a solid globe like Earth. Instead, Jupiter is mostly of gas, and deeper down, crushing pressure squeezes that gas into strange forms of matter. The planet spins so quickly that a single Jovian day lasts just 10 Earth hours, even though the world is more than 100 times larger than ours. This fast rotation flattens Jupiter slightly at the poles and bulges it around the middle. Across its surface, you see colorful bands racing around the planet, driven by winds faster than any hurricane on Earth. These stripes are not simply decorations, but the result of powerful jet streams encircling the globe. Even though Jupiter seems familiar from pictures, it is far stranger and more complex than most of us ever realize. Its size alone would be enough to lift it into legend, yet the secrets hidden inside it are far more intriguing. To understand Jupiter is to step into a realm where the rules of matter and energy behave in ways we rarely experience. And in the moments ahead, we will drift deeper into this enormous world and discover how much it still hides from us. Jupiter's gravity is the quiet force that holds its entire system together. It is more than twice as strong as the gravity you feel on Earth. Yet, because Jupiter is made of gas, you could never stand on it. If you tried to land, you would sink deeper and deeper into its thick atmosphere, surrounded by clouds that grow denser with every passing moment. The deeper you travel, the more the pressure increases, until ordinary matter behaves in extraordinary ways. This immense gravity shapes Jupiter into an oblate form, flattened slightly at the poles and stretched around the equator. It also keeps the planet spinning in a way that stirs its atmosphere into fast-moving streams. These rapid winds race in opposite directions, forming the dark and light bands wrapped around the globe. Each band is a river of gas flowing at hundreds of miles per hour. As the different currents slide past each other, they create swirling boundaries that can last for years. Scientists believe that the planet's rotation, combined with the heat rising from deep inside, powers these enormous flows. Jupiter produces more heat than it receives from the sun, releasing ancient energy left over from the birth of the solar system. This heat slowly escapes through the atmosphere, helping to drive storms and maintain the planet's dramatic appearance. Even though Jupiter seems peaceful from afar, its atmosphere is alive with motion. Winds, currents, and invisible forces work together to sculpt its colorful patterns. On Jupiter, a change in temperature or pressure can influence whole regions of the planet, reminding us just how enormous this world truly is. In the next moments, we will leave the outer layers behind and drift toward Jupiter's hidden interior, where the mysteries grow even deeper. When you look at Jupiter, you see only the thinnest outer layer of its atmosphere. Beneath the bright clouds lies a world that no human eye has ever seen directly. There is no solid ground, no place to land, and no single moment when gas turns into rock. Instead, Jupiter's interior changes smoothly from gentle clouds into crushing depths. The upper layers are made mostly of hydrogen and helium, the same ingredients found in the sun. As we drift downward, the pressure increases so quickly that the gas becomes thick and warm. Soon, the molecules are squeezed so tightly together that the atmosphere behaves more like a deep ocean than a sky. This region may extend thousands of miles below the visible clouds. Scientists believe that the deeper you go, the more the hydrogen transforms into a strange state of matter. At enormous pressure, hydrogen stops acting like a familiar gas and turns into a hot, dense fluid. This fluid is unlike anything we can make easily on Earth. It may conduct electricity, create powerful currents, and help fuel Jupiter's immense magnetic field. The temperature rises steadily as you descend, climbing far above the heat of any place on our planet. Even though the layers blend smoothly into one another, each step downward reveals a realm more extreme than the last. Jupiter's interior is not a place where life could survive, yet it is one of the most fascinating environments in the solar system. Here, matter itself behaves in unfamiliar ways, shaped by pressure so great that it tests the limits of physics. And deeper still lies a form of hydrogen that is even more extraordinary, waiting in the shadows of Jupiter's core. As we drift farther into Jupiter's depths, the pressure becomes strong enough to transform the planet's material into something astonishing. Hydrogen, which floats gently in Earth's sky, is forced into a dense liquid that behaves like flowing metal. This metallic hydrogen is one of the most unusual substances in the entire solar system. It is so compressed that its electrons move freely, allowing it to conduct electricity with ease. Scientists believe that this vast ocean of metallic hydrogen swirls slowly inside the planet, creating electrical currents. Those currents may be responsible for Jupiter's powerful magnetic field, which is far stronger than anything found on Earth. The deeper you go, the more extreme the conditions become. Temperatures may rise to tens of thousands of degrees, matching the outer layers of small stars. The pressure grows so immense that even atoms themselves are pushed into new arrangements. Although we cannot send a probe to these depths, computer models and laboratory experiments give us clues about what lies hidden there. Jupiter's core remains one of its most mysterious features. Some scientists think the core may be a dense, rocky region wrapped in metallic hydrogen, while others believe it could be a thick, slushy layer of heavy elements mixed with fluid. Whatever its true form, the core is buried so deeply that no direct measurement has ever reached it. Even advanced spacecraft can only sense its presence through tiny changes in Jupiter's gravity. These signals hint at a core much larger and more complex than once imagined. Down here, near the heart of Jupiter, the boundaries between solid, liquid, and gas blur into something entirely new. The planet's immense weight squeezes matter into forms that challenge our understanding, reminding us how different gas giants are from worlds like Earth. When people imagine a planet, They often picture a place with ground beneath their feet. But Jupiter has no surface in the way Earth or Mars does. If you tried to land on Jupiter, there would be no moment when you touched solid ground. Instead, you would sink smoothly into deeper and thicker layers of gas. The upper clouds look like a surface from far away, but they are only floating patterns made of ammonia and other simple chemicals. Beneath those clouds lies a massive atmosphere that grows warmer and denser with every mile downward. The pressure increases so steadily that your spacecraft would be crushed long before reaching the metallic hydrogen layers. Jupiter does not have a sharp boundary where gas stops and liquid begins. The transitions happen gradually, like moving from cool air into warm water in a deep ocean. Even deeper, the atmosphere becomes so dense that it acts like a fluid, though it is still made of the same hydrogen and helium that drift through space. The concept of a surface becomes meaningless in a world held together by such overwhelming pressure. This is one reason Jupiter fascinates scientists. It challenges our everyday ideas of what a planet should look like. The lack of a solid surface also means storms can form and evolve without the limits found on terrestrial planets. There are no mountains to block winds, no continents to break the flow of currents, and no oceans to absorb heat. Everything moves freely, shaped only by temperature, pressure, and the planet's fast rotation. In this boundless environment, storms can grow to sizes larger than Earth and survive for centuries. And as we drift away from Jupiter's hidden interior, we rise toward the region where those storms rule the planet's appearance. The most famous feature on Jupiter is a storm so large that our entire planet could fit inside it. This enormous oval is known as the Great Red Spot, and it has been swirling for centuries. Early astronomers first noticed it through small telescopes in the 1600s, long before electricity or airplanes existed on Earth. Since then, the storm has never disappeared. Its powerful winds circle around a deep vortex, moving faster than the strongest hurricanes found on our world. Inside the storm, gases rise and sink in vast spirals, creating swirling patterns that change slowly over time. The red color of the Great Red Spot remains one of its greatest mysteries. Some scientists think sunlight may react with chemicals in the atmosphere to produce reddish tones. Others believe lightning or ultraviolet radiation might alter the particles drifting through the storm. Whatever the cause, the color gives the storm a dramatic appearance against the lighter bands of Jupiter's atmosphere. The Great Red Spot is shaped by the planet's rapid rotation and complex system of jet streams. These fast-moving bands of wind create boundaries that trap the storm, preventing it from drifting freely across the planet. This confinement may be one of the reasons the storm has lasted so long. Over the years, the Great Red Spot has changed in size. It has slowly been shrinking, though it remains enormous and powerful. Despite its changes, the storm continues to be one of the most iconic sights in the solar system. When spacecraft fly past Jupiter, they capture detailed images of the storm's churning clouds, revealing shapes and textures that look almost like brushstrokes on a canvas. Yet beneath the beauty lies an immense system of winds and pressure that would be far too violent for any vehicle to survive. As we drift onward, we leave this legendary storm behind and explore the other atmospheric patterns that make Jupiter a world of endless motion. Jupiter's bands are among the most recognizable patterns in the night sky. These stripes wrap around the entire planet, forming alternating zones of pale and dark colors. Each band represents a massive jet stream where winds rush in opposite directions at tremendous speed. Some of these winds move faster than 300 miles per hour, pushing clouds along like flowing rivers. The light-colored regions are called zones, and they tend to rise upward, forming tall, bright cloud tops. The darker regions are known as belts, where air sinks and clouds form in deeper layers. The boundaries between zones and belts create turbulent regions full of swirling waves. When these currents meet, they twist and stretch into complex shapes that can last for months or even years. The colors themselves come from chemicals such as ammonia and sulfur, which reflect sunlight in different ways. As the gases mix and rise, they form patterns that shift from white to brown, red, and even subtle shades of blue. Little storms appear across the bands as bright ovals or small dark spots, each one shaped by the winds surrounding it. Some of these storms merge, while others drift along the jet streams until they fade away. Jupiter's rotation plays a key role in maintaining these bands. The planet spins so quickly that its atmosphere is stretched into long, narrow flows rather than large circular patterns like those on Earth. Deep below the visible clouds, similar jet streams may continue for thousands of miles. Because the atmosphere is so deep, these winds can extend far beyond what we can see from space. The result is a layered system that behaves like a massive rotating machine. Even though the bands appear calm from a distance, they hide powerful motions that constantly reshape the planet's appearance. As we continue our journey, we will explore the lesser-known storms that circle Jupiter's poles, where the winds create patterns unlike any found on Earth. Near Jupiter's poles, the atmosphere takes on a completely different character. Instead of long horizontal bands, the clouds form swirling clusters of enormous cyclones. These storms arrange themselves into elegant geometric patterns, shaped by forces we are only beginning to understand. At the North Pole, several cyclones form a tight ring around a central storm. At the South Pole, the arrangement is similar, though the number and size of the storms differ slightly. Each cyclone is as wide as a continent on Earth and reaches deep into the atmosphere. Despite their size, they remain stable, holding their positions for years without drifting apart. The winds inside these polar storms can reach remarkable speeds, twisting through spirals that create beautifully textured cloud patterns. From above, they look like giant flowers blooming in slow motion across the planet's poles. These storms do not crash into one another as hurricanes often do on Earth. Instead, they keep a careful distance, spinning side by side in a delicate balance. Scientists believe the combination of Jupiter's rotation, internal heat, and deep atmosphere helps maintain this stability. Farther from the poles, smaller storms appear in various shapes and sizes. Some form bright white ovals, created by rising clouds of ammonia crystals. Others form darker spots, shaped by sinking air and chemical reactions happening deep below. Jupiter also experiences rare events known as disturbance outbreaks, where new storms erupt and spread across the belts. These outbreaks can reshape entire regions, altering the appearance of the planet for months at a time. Together, the poles and the belts reveal how dynamic Jupiter truly is. Every region is in motion, from the bright equatorial bands to the mysterious cyclones near the poles. And as we leave the storms behind, we begin to approach one of the most powerful features in the entire solar system. Jupiter's magnetic field is one of the most powerful natural forces in the solar system. It is so large that it stretches far beyond the orbits of many of Jupiter's moons, forming a magnetic bubble bigger than the Sun itself. This enormous structure is called the magnetosphere, and it shields the planet from a constant stream of charged particles flowing from the Sun. The magnetic field is generated deep inside the planet, where metallic hydrogen moves in slow, swirling currents. These currents create an immense dynamo, similar to the one inside Earth, but far stronger. If you could see Jupiter's magnetosphere with your eyes, it would appear as a gigantic, invisible halo reaching millions of miles into space. Inside this magnetic region, charged particles race around at high speeds, forming belts of radiation far more intense than any found near Earth. These radiation belts are strong enough to damage spacecraft, and any future missions exploring Jupiter must carefully avoid the most dangerous regions. The magnetic field also interacts with the planet's moons. As the moons travel through the magnetosphere, they create electrical currents that connect them directly to Jupiter's upper atmosphere. Io, the volcanic moon, produces some of the strongest interactions, generating powerful beams of energy that flow along magnetic lines. These beams crash into Jupiter's poles and create brilliant auroras. While Earth's northern lights glow softly across the night sky, Jupiter's auroras are much larger and brighter. They shine constantly, shaped not only by sunlight, but also by the movement of charged particles inside the magnetosphere. This magnetic power gives Jupiter a presence in space unlike any other planet. It influences moons, shapes radiation fields, and creates glowing light displays that would be breathtaking to anyone able to see them up close. In the next segment, we will drift toward these shimmering lights and explore how Jupiter's magnetosphere paints the poles with color. Jupiter's auroras are among the most powerful light shows in the solar system. They glow near the poles as rings of bright energy, formed when charged particles crash into the planet's upper atmosphere. Unlike Earth, where auroras appear only during strong solar activity, Jupiter's auroras shine almost all the time. This steady glow is fueled not only by the solar wind, but also by the constant motion of particles trapped inside the magnetosphere. Some of these particles come from Io, the volcanic moon, which releases clouds of charged material into space. As Io moves through Jupiter's magnetic field, it creates an electrical connection that guides energy toward the planets. The result is a bright circle of light called the Io footprint, glowing like a permanent spark in Jupiter's sky. Other moons also leave their marks, producing smaller footprints that drift through the auroras as the moons move along their orbits. These glowing patterns reveal how tightly the moons and the magnetosphere are linked. Far above the atmosphere, Jupiter's radiation belts swirl with immense power. These belts contain high-energy particles moving at speeds close to the speed of light. They are so intense that spacecraft must follow careful paths to avoid being damaged. Even brief exposure to the strongest regions could overwhelm sensitive instruments. Yet these belts help us understand the strength of Jupiter's magnetic field. The field traps particles and holds them in place, forming rings of radiation that encircle the planet. Studying these belts gives scientists clues about how the magnetosphere changes over time. Together, the auroras and radiation belts show that Jupiter is not only a planet, but also a vast magnetic engine. Its energy shapes everything around it, from the glow above its clouds to the invisible forces stretching millions of miles into space. As we move forward, we leave this magnetic world behind and drift toward the many moons that orbit Jupiter like a family of tiny worlds. Jupiter is not only a planet, but the center of a vast miniature solar system. More than 90 known moons orbit this giant world, each following its own quiet path through space. Some are small and irregular, shaped like drifting stones left over from the early days of the solar system. Others are smooth and round, formed by the same forces that shaped planets. Together, they create a complex community of worlds that move in harmony around Jupiter. The smallest moons are called irregular satellites. Many of them are captured objects, pulled into Jupiter's orbit long ago by the planet's enormous gravity. These tiny moons often have tilted or stretched orbits, and some even travel in the opposite direction of Jupiter's rotation. Because they are so small, they do not have enough gravity to shape themselves into spheres. Instead, they remain lumpy and angular, reminders of a time when the solar system was filled with loose, drifting debris. Farther inward, closer to Jupiter, the moons become larger and more orderly. The 4 biggest moons are called the Galilean moons, named after the astronomer who first saw them through a small telescope in 1610. Their discovery changed our understanding of the universe, showing that not everything revolves around Earth. These moons are Io, Europa, Ganymede, and Callisto, and each one is a world with its own unique character. They vary from volcanic landscapes to icy oceans and ancient cratered surfaces. Even though they orbit the same planet, they could not be more different from each other. As we move to the next segment, we will drift closer to these 4 remarkable moons and explore how they became such special places in Jupiter's wide domain. The 4 Galilean moons are among the most remarkable objects in the entire solar system. Each one is large enough to be a world of its own, shaped by gravity, heat, and time. Together, they orbit Jupiter in a steady pattern, locked into a delicate rhythm that keeps their motions perfectly balanced. The closest of the 4 is Io, a moon so active that its entire surface is reshaped by constant volcanic eruptions. Its bright colors come from sulfur and molten rock, spread across plains and mountains that never stay the same for long. Farther out lies Europa, a smooth and icy world that hides a deep ocean beneath its frozen surface. Scientists believe this ocean may contain more water than all of Earth's seas combined. Europa's cracked surface patterns hint at tides and shifting ice driven by the moon's internal heat. Next comes Ganymede, the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is so massive that it generates its own magnetic field, a rare trait among moons. Its surface is a mix of dark regions and bright, grooved terrain shaped by ancient geological forces. The 4th moon is Callisto, the farthest of the group and the most heavily cratered. Callisto's surface preserves some of the oldest scars in the solar system, a frozen record of impacts stretching back billions of years. Together, these 4 moons demonstrate how diverse a single planetary system can be. They range from fiery landscapes to hidden oceans and ancient ice fields, offering glimpses into both violent and peaceful histories. As we leave the overview behind, we begin a closer journey toward Io, the closest of Jupiter's great moons and one of the most extreme places ever discovered. Io is the most volcanic place we know of, not only in our solar system, but anywhere in the universe that we have explored. Its entire surface is alive with activity, shaped by constant eruptions that throw fountains of molten rock high into space. These eruptions are so powerful that they can rise hundreds of miles above the surface before falling back in glowing arcs. Io's bright colors come from sulfur and other minerals heated and spread across the landscape. Yellows, reds, and deep blacks cover the moon like the strokes of a vast cosmic painting. Instead of quiet mountains or smooth plains, Io is covered with volcanic pits, long lava flows, and towering plumes of gas. But what makes Io so active is not its size or its composition. The secret lies in the constant gravitational pulling from Jupiter and the other large moons. As Io orbits, it is stretched and squeezed over and over by these powerful forces. This kneading motion generates intense heat deep inside the moon, melting rock and driving the volcanic eruptions. The process is called tidal heating, and on Io, it is strong enough to keep the interior partly molten at all times. Even from space, spacecraft have seen glowing spots on the surface, signs of lava lakes so hot that they shine through the night side of the moon. Some lava fields may be larger than entire countries on Earth. When volcanoes erupt, they create enormous plumes that rise above the surface and cast long shadows across Eo's plains. These plumes form thin, temporary atmospheres that collapse again once the eruptions slow. Despite its violent appearance, Io is a world full of scientific clues about heat, gravity, and geological change. Its surface may look harsh, but it reveals how powerful forces can shape a moon into something completely unique. In the next segment, we will explore how Io interacts with Jupiter itself, creating a ring of glowing energy that stretches across the space between them. Io does not exist in isolation. Its constant volcanic eruptions play a major role in shaping the space around Jupiter. When volcanoes release gas into the thin atmosphere, much of that gas escapes into space and becomes ionized by sunlight and magnetic forces. These charged particles form a giant ring around Jupiter called the plasma torus. This torus is like an invisible donut of energetic material that encircles the planet along Io's orbit. The plasma inside the torus moves quickly, guided by Jupiter's powerful magnetic field. Because Io travels through this magnetic environment, it creates a strong electrical connection with the giant planet. As the moon moves, it acts like a conductor, generating electrical currents along magnetic lines that stretch all the way to Jupiter's poles. These currents create bright spots in the planet's auroras, known as Io footprints. Each footprint is a glowing signature that traces Io's exact path through the magnetosphere. These glowing marks help scientists study the relationship between the moons and Jupiter's magnetic field. They show how energy flows from volcanic eruptions on Io to the shimmering lights far above Jupiter's clouds. Io's plasma torus also affects the other moons nearby. It fills their surroundings with charged particles that can alter their surfaces and shape their interactions with the environment. For spacecraft, the torus is a region of high radiation, requiring careful navigation to avoid damage. Yet, despite the risks, studying this region teaches us how magnetospheres behave and how moons can influence giant planets. Io's activity makes it one of the most dynamic moons in the solar system. It is a world caught between gravity, heat, and magnetic power, constantly creating new landscapes and sending energy outward into space. As we drift away from this fiery moon, our journey carries us toward Europa, a world shaped not by volcanoes, but by ice and water hidden beneath its surface. Europa is one of the most mysterious worlds orbiting Jupiter. From a distance, it looks calm and pale, covered in smooth ice that reflects sunlight like frosted glass. But beneath this quiet surface lies something extraordinary. Scientists believe that a deep, global ocean rests below the icy shell, an ocean that may contain more water than all of Earth's oceans combined. The surface of Europa is crisscrossed with long, dark lines, stretching for hundreds of miles across the moon. These lines are fractures in the ice, created as the surface slowly shifts and bends. The shifting is caused by tidal forces from Jupiter, which gently stretch and squeeze Europa during its orbit. This motion generates heat inside the moon, preventing the ocean below from freezing completely. In some places, warm water may rise and push upward, creating patterns and ridges across the surface. The ice crust may be only a few miles thick in some regions, while in others it could extend much deeper. Still, signs of movement show that the shell is active, with sections that break apart and freeze again over time. The possibility of a liquid ocean makes Europa one of the most intriguing places to search for life. Its water is protected from radiation by the thick ice above it, creating a stable environment deep below the surface. Heat from the moon's interior could drive currents, mix nutrients, or create warm pockets similar to hydrothermal vents on Earth's ocean floor. While we do not know what might exist in Europa's hidden waters, the moon offers the right ingredients for a stable and long-lasting ocean. From above, Europa may look calm and frozen, but inside it carries the energy and potential of a living world. In the next segment, we will explore the clues that suggest water occasionally escapes to the surface in the form of mysterious plumes. Europa's icy shell may look still, but careful observations reveal signs of activity just beneath its surface. One of the most intriguing clues comes from faint plumes of water vapor that may erupt through cracks in the ice. These plumes rise high above the surface before falling back down as frozen droplets. If they are confirmed, they would offer a direct path to sample Europa's ocean without drilling through miles of ice. The cracks on Europa form long ridges and double lines, as if the ice has been pulled apart and then pushed back together. Some ridges may form when warm water or slushy ice rises from below and refreezes near the surface. Other cracks may be created by tidal flexing, as Jupiter's gravity stretches the moon during each orbit. This constant stretching generates heat inside Europa, keeping the ocean beneath the surface from freezing solid. The heat may also help circulate water deep below, feeding gentle currents that shape the ice from beneath. In some places, the surface appears smooth and fresh, suggesting that new ice has formed recently. These newer surfaces reflect sunlight differently, appearing brighter than the older, more weathered regions. Such areas hint at ongoing activity where ice plates may break apart and move slowly over time. The possibility of plumes is especially exciting. Spacecraft have detected hints of water vapor near Europa, and some faint signals resemble those seen near geysers on other icy moons. If confirmed, the plumes would show that the ocean communicates with the surface in active ways. This would make Europa a prime target for future missions seeking signs of habitability. Even though Europa is far from the warmth of the sun, the energy within its interior keeps it alive with gentle motion. As we journey onward, our path leads to Ganymede, the largest moon in the solar system, and a world filled with unexpected features. Ganymede is the largest moon in the entire solar system, even bigger than the planet Mercury. Its size alone makes it remarkable, but Ganymede holds another rare distinction. It is the only moon known to generate its own magnetic field. This magnetic field interacts with Jupiter's larger field, creating a complex environment filled with charged particles and gentle auroras dancing near the poles. Ganymede's surface is divided into two main types of terrain. Dark, ancient regions are covered in impact craters, showing that parts of the surface are billions of years old. In contrast, bright, grooved regions stretch across the moon like frozen scars. These grooves may have formed when tectonic forces pulled and twisted the icy crust. The patterns suggest that Ganymede once had, and may still have, a warm interior capable of driving geological change. Deep beneath the surface, scientists believe Ganymede hides a layered ocean. The ocean may be sandwiched between stacks of ice, with liquid water trapped between frozen layers. This unusual structure is created by the changing pressures inside the moon. Even though Ganymede is colder than Europa, it may still contain more water overall. The combination of size, magnetism, and hidden seas makes Ganymede a world unlike any other moon. Icy cliffs, ridges, and deep craters shape its surface, creating a landscape frozen in time. Yet the moon's interior tells a story of activity, heat, and complexity that continues even now. As we leave Ganymede behind, we drift outward to Callisto, a quieter moon that preserves the most ancient history in Jupiter's vast domain. Callisto is one of the most ancient and untouched worlds in the solar system. Its surface is so heavily cratered that it looks almost the same today as it did billions of years ago. Every crater is a preserved memory of an impact long ago, frozen into the ice and rock that make up the moon's crust. Because Callisto has very little internal heat, its surface does not change much over time. There are no major mountains forming, no volcanic eruptions, and no shifting plates to erase the scars of the past. This quiet nature makes Callisto a time capsule of the early solar system. Scientists study its surface to learn what conditions were like when planets and moons were still taking shape. The moon's many overlapping craters create complex patterns, some of which spread across hundreds of miles. One of the largest impact features is called Valhalla, a circle of rings created by a powerful collision long ago. The impact sent waves through the moon's crust, forming ripples that extend outward like the rings on a pond. Despite its quiet surface, Callisto may still hide surprises beneath its icy shell. There are hints that a deep underground ocean could exist far below the surface, warmed by just enough internal heat to remain liquid. If this ocean is real, it would make Callisto another candidate for water-filled worlds in Jupiter's family. But unlike Europa or Ganymede, any ocean on Callisto would be buried under a thick layer of ice, protected from radiation by great depth. Callisto's ancient appearance gives it a peaceful and distant beauty. It drifts on the edge of Jupiter's system, far from the intense magnetic fields closer to the planet. Because of its stability and gentle environment, Callisto has been suggested as a possible future base for human exploration. Its calm surface and isolation make it a quiet neighbor in the bustling Jovian system, a world that has watched billions of years pass in silence. As we leave Callisto behind, our journey through Jupiter's realm draws to a gentle close, ending with a final reflection on this vast and mysterious system. Jupiter has rings, although most people never see them. They are so faint that even large telescopes on Earth can barely detect them. The rings were discovered in 1979 when the Voyager spacecraft passed behind Jupiter and looked toward the Sun. The backlight revealed a thin, glowing band made of tiny dust particles. Unlike Saturn's bright, icy rings, Jupiter's rings are dark and delicate. They are made mostly of microscopic grains kicked up from the surfaces of small inner moons. When meteoroids strike these moons, they blast dust into space. Jupiter's gravity then pulls this dust into a thin, circular sheet that gently arcs around the planet. The system has several parts. The innermost is called the halo ring, a faint cloud of dust that glows softly near the planet. Outside the halo lies the main ring, flat and narrow, made of tiny dark particles that reflect very little sunlight. Farther out are the gossamer rings, created by dust drifting from the tiny moons Amalthea and Thebe. These gossamer rings are so thin that they are almost invisible unless illuminated from behind. Most of the particles in Jupiter's rings are extremely small, often no larger than smoke or fine ash. Because they are so light, they are easily pushed around by radiation, electric forces, and Jupiter's vast magnetic field. This makes the rings dynamic and ever-changing. Dust slowly drifts inward toward Jupiter, falling into its atmosphere over time. New dust arrives constantly as fresh impacts strike the small moons. In this way, the rings are always being renewed and always fading at the same time. From a distance, the rings look calm and simple, but close up, they reveal a delicate balance of collisions, sunlight, magnetic forces, and gentle motion. They show that even a giant planet known for storms and power can also host something as subtle as a quiet halo of dust. In the next segment, we will move deeper into this ring system and explore how the tiny moons near Jupiter shape every grain of dust drifting through this twilight zone. Jupiter's rings exist because of its small inner moons. These moons are not large or bright, yet they play an important role in creating and maintaining the delicate dust around the planet. The closest moon, called Metis, orbits just above the cloud tops and moves faster than any other moon in the Jovian system. A little farther out is Adrastea, a small irregular moon with a rugged surface. Both Metis and Adrastea help feed the main ring. When tiny meteoroids strike these moons, they release clouds of dust. The particles spread out along the moon's orbits and eventually form a smooth, thin ring. Because the dust grains are so small, they are quickly influenced by sunlight. Radiation pressure slowly pushes some of the particles outward, while others drift inward. Jupiter's powerful magnetic field adds even more movement, guiding electrically charged grains into gentle spiral shapes. Together, these forces constantly rearrange the ring structure. Farther from Jupiter, two additional moons, Amalthea and Thebe, produce the gossamer rings. These rings extend far into space, forming pale, ghost-like layers that are hard to see directly. Under the right lighting, they glow softly, revealing long curtains of drifting dust. Because the grains are so thinly spread out, the gossamer rings appear almost transparent. Spacecraft images show how the rings brighten when sunlight strikes them from behind. From other angles, they almost vanish into the darkness. Each ring particle slowly orbits Jupiter, completing a path in only a few hours. Over time, many grains spiral downward and disappear into the planet's atmosphere. New dust is added in small bursts of impacts, creating a quiet cycle of renewal that continues year after year. Even though these rings are faint, they remind us that big things in space are often accompanied by small and subtle details. In their own gentle way, Jupiter's rings show how tiny grains can drift together to form something beautiful, fragile, and ever-changing. Jupiter was the first planet to form in our solar system. It began growing while the Sun was still young and surrounded by a wide disk of gas and dust. Small pieces of ice and rock clumped together, forming a core that grew larger with time. When the core reached a critical size, its gravity became strong enough to pull in huge amounts of surrounding gas. This process happened quickly on cosmic timescales. Within a short period, Jupiter became the giant we see today. Its formation influenced everything else in the solar system. The growing planet stirred the disk of material around it, affecting the orbits of young asteroids and shaping the structure of the early solar neighborhood. Some scientists believe Jupiter migrated inward during its early life. This idea is known as the Grand Tack hypothesis. According to this model, Jupiter moved closer to the Sun before reversing direction and drifting outward again. If this migration really happened, it would have had major consequences for the inner planets. The movement of the giant planet might have prevented the formation of a super-Earth close to the Sun. It may also have shaped the mass and orbits of Mars and the asteroid belt. As Jupiter grew, it cleared out large regions of the disk, pushing some objects away and pulling others toward itself. Many icy bodies from the outer solar system may have been redirected inward. These icy visitors could have delivered water to the young Earth, helping to create the oceans we know today. Jupiter's early presence also reduced the number of large impacts hitting our planet. Its gravity captured or deflected many wandering asteroids and comets. Without Jupiter, Earth might have endured more catastrophic collisions. In this way, Jupiter acted as a stabilizing force, shaping the environment where life could eventually appear. The story of Jupiter's birth is a story of motion, growth, and powerful influence that continues even now. In the next segment, we will explore how Jupiter shaped the early solar system's chaos and helped sculpt the worlds that formed around it. After Jupiter formed, the solar system entered a period of turbulence. The young sun was still settling, and the planets were moving in unstable orbits. Jupiter's enormous gravity played a major role in this early chaos. It shifted the orbits of nearby asteroids, sending some into the inner solar system and ejecting others into deep space. This movement helped shape the asteroid belt into the scattered region we see today. The giant planet also influenced the formation of Saturn. As both planets grew, they interacted through gravity, creating new orbital patterns. These patterns may have stabilized their motions, locking them into a balanced configuration that remains to this day. Jupiter's influence extended even farther. Countless icy bodies beyond Saturn were nudged into new paths. Some entered elongated orbits that carried them close to the Sun. These objects became early comets, bringing water and organic molecules to the young inner planets. Jupiter also protected the forming Earth by absorbing or deflecting many of these objects. Its strong gravity acted like a giant shield. This shield reduced the number of catastrophic impacts Earth would have faced. Without Jupiter, the early solar system would have been more violent and unpredictable. As the system stabilized, Jupiter settled into its current orbit, and the young worlds around it continued to grow. Earth cooled, oceans formed, and life eventually emerged. Jupiter remained in the background, continuing to shepherd comets and shape the paths of wandering bodies. Today, Jupiter still influences the solar system. Its gravity maintains the asteroid belt, guides comet families, and affects the orbits of nearby planets. The story of Jupiter is the story of the solar system itself, from its earliest chaos to its quiet present. It reminds us that even distant giants can leave lasting marks on the worlds around them. Our quiet journey through Jupiter and its many worlds has reached its final moments. We have drifted past swirling storms, glowing auroras, hidden oceans, and ancient landscapes shaped by time. Each part of Jupiter's realm holds something unique, from the deep metallic heart of the giant planet to the icy surfaces of its most distant moons. Jupiter itself is a world of immense power, shaping the space around it through gravity, magnetic fields, and endless motion. Yet its moons reveal a gentler side, full of calm ice fields, quiet valleys, and oceans kept warm by forces deep within. These worlds drift together in a delicate balance, orbiting a planet that has watched over them since the beginning of the solar system. As we leave Jupiter behind, we carry with us the knowledge that even the largest and wildest places in space contain moments of peace and quiet beauty. In the distance, the giant planet fades into soft bands of color, turning slowly beneath its storms and glowing lights. And as our journey ends, we settle into a moment of calm, knowing that the mysteries of Jupiter will continue to inspire wonder for generations to come.